from the context, in some books you may see the notation L1 x S mu instead of L1 mu, okay, because this sigma algebra and this measure is important, and this space related to all of these objects, okay, x, S and mu. And this is the definition of L1. Suppose x is mu is a measure space if f from x to real extended line is measurable, then the L1 norm of f is denoted by norm1 of f and is defined by this integral. The norm of f, norm1 of f, equal to the integral of absolute value of f with respect to mu, so that this norm is depend on mu, so that we see that we can write by this notation, okay. This one is for the power of this, because the power of the absolute value of f equal to 1, okay. And we take integral with respect to mu. The Lebesgue space L1 mu is defined by the set of all S measurable functions from x to r such that this norm is finite, okay. The set of all S measurable functions from x to r such that this norm is finite. So that L1 is the set of all mu integrable function. Integrable function, okay? Let me take some example. L1 mu for functions that take on only finitely many values. More exactly, these functions, okay? Suppose x is mu is a measure space and E1, E2, En are disjoint subsets of x. Suppose A1, A2 up to the end are these distinct non-zero real numbers. Then this function, a linear combination of characteristic functions, okay, belong to L1 if and only if all of these sets belong to S and mu of ek is finite for all k, okay. It is clear that this sets must belong to S, because we know that, and in the previous, sorry, let me a minute. Tamam mı? Evet, bu bir soru, hadi bu. Bu var mı? Şaka. Evet, چه هستی اونجا؟ چی بود؟ ما کلاس هستیم باید برید که موره الان کلاس هم شروع شد ساعت 1:30 تا 2:30 من کلاس دارم نمیتونی چی خواهد اگه میخوایی بری باید ماشین بذاری بیرون سویج رو بدی به این دوازه یلکی دارم بگیرم باشه کن الان کلاس هم مثل تو عصر طول میکشه الان صداش افتاد دیگه بهتره شد قبلا هم جوش شده بودم باشه پس حالا ببین من مثلا یه ساعت دیگه که بعدم کلاسای بعدی شروع میشم اون دیگه آدم یه جور دیگه هم میبرم دیگه باشه باشه باش قربان ممنون خدا sorry I'm very sorry because we know that and we see that for example for each E we know that E is an element of S if and only if phi of E is S measurable. Okay? So that this condition implies that and guarantees that this function is S measurable. And this condition guarantees that the integrals of this is finite. Okay? Furthermore, this norm equal to this summation. Because the integral of f d mu equal to the integral of this summation, for example a1 to an, a1 phi of e1 plus an phi of en d mu, and this is equal to this a1 e1 plus absolute value of an phi of en d mu. Okay, and this is equal to this linear combination E1 up to the En, and this is equal to absolute value of A1 mu of E1 plus absolute value of an mu of en. So by our assumption that all of this mu of E1, mu of E2 up to mu of En is finite, this is finite. Okay, so that if mu of E1 up to mu of En is finite, then we see that this integral is finite because this integral equal to this summation. Okay, and conversely if the integral of f, integral of absolute value of f, the mu is finite, then this summation must be finite, and so all of this must be finite. Mu of E1, sorry, Mr. Abdul Salam, do you have any question? Dear students, do you have my voice? Do you have my voice and do you see the image? Dear students, do you have my voice? Do you have my voice? Okay. With respect to counting measure, it is not that x equal to natural number and mu is counting measure. Okay. Okay. Properties of the L1 norm. Suppose X S mu is a measure space and F and G belong to L1 of mu. Then these four properties is very obvious. One, the norm 1 of any S measurable function is non-negative because norm 1 equal to this. by our definition, nor1 of f okay, equal to this integral and since this is positive, this integral is positive, we see that the integral of any non-negative function is non-negative, okay? The Lebesgue integral of any non-negative function is non-negative. The Lebesgue integral of any non-negative functions is non-negative. Okay? We use this fact that we see in the previous semester and previous sessions. And the nor1 of f equal to 0 if and only if f equal to 0 almost everywhere. And we see this again because this equal to 0 equal to this integral equal to 0, okay? And this holds if and only if this function equal to 0 almost everywhere. And this is equal to this, okay? On the other hand, the mu of this set equal to 0. Mu of this set, the set of all sets that f of x is non-zero, must be 0. And also we see these properties and these properties because this nor equal to this integral, and this is equal to this, and this is equal to this because this is nor1, okay? This is nor1 of f, and the nor1 of f plus g equal to this integral, and by triangle inequality this is less than or equal this integral, and this is equal to these two integrals that we see all of these in real analysis 1, okay? In real analysis 1 course. For this, please note that if we know that if, for example, h1 is less than h2, then the integral of h1 is less than the integral of h2, okay? This is our h1 for example, and this is h2. By triangle inequality, because this is less than this function, we have this inequality, and this is equal to this by theorem. Okay, you can find the number of this theorem in your book. Okay, these properties shows that this is a norm function. Okay, this is a norm. So norm 1 is a norm function on L1. Okay, and L1 and this norm is a normed space. Normed space. This normed space is a Banach space, or every Cauchy sequence is converged sequence. Every Cauchy sequence in this space have a limit in this space. Okay, have a limit in this space. This norm is complete on L1, and we have some important propositions such as is approximation by simple functions. Suppose mu is a measure and f belonging to L1, then for every epsilon there exists a simple function g such that the norm of f minus 3 norm 1 is less than epsilon, so that we can approximate any integrable function, any element of L1 with a simple function. This simple function is arbitrary near to f because this norm is less than epsilon and epsilon is arbitrary. Okay, but g is simple function. G is a simple function. G is a simple function such as is, for example. Okay, okay, so that this is very important for each epsilon. If f belong to L1, okay, then for each epsilon we can find a simple function g such that this norm is less than epsilon. Okay, and this proof is easy by previous propositions. Suppose epsilon is an strictly positive real numbers, then there exist simple functions g1 and g2 such that g1 is less than f plus and g2 is less than f minus, and these two integrals less than epsilon divided by 2. where we have used this proposition 3.9, okay, that you can see this. Let me know, this is the page number 96, okay. Please note that we use this proposition. Any S measurable that are non-negative value, that have a non-negative value, f from x to 0 infinity. This integral equal to this supremum. So that for each epsilon there exists one of these summation that the difference from this and this is less than epsilon for each epsilon, okay? And this simple function is less than f. And also this simple function are non-zero, okay? This is the direct consequence of this proposition. For each epsilon there exists one of these simple functions because by this we can write that for each epsilon there exists a simple function such as this. Cj for example x rj. Okay, such that this G is between 0 and f plus, because f plus is an S measurable function that is non-negative, okay? And this G is non-negative by this assumption. These coefficients are non-zero, so that this function is non-negative, so that this function is non-negative, okay? And also these two have this property that this minus this is less than epsilon. But this is equal to the integral of f minus integral of g, because this is the integral of this function, okay? This is simple function and this is its integral, and this is equal to the integral of f minus g d mu, and this is equal to the integral of this, because this is positive. By this assumption this is positive, okay? So its absolute value equal to itself, and this is equal to this null. So that we find a simple function such as g such that the null of f minus g normal 1 is less than epsilon. Okay, this lead to these properties, and we use these propositions okay. Because f plus and f minus are non-negative S measurable functions, for both of these functions there exist functions such as g1 and g2 by these properties and these properties. Now let we consider g equal to g1 minus g2. Then g is a simple function too, and this simple function belongs to this space L1, and the norm 1 of f minus g equal to the norm 1 of this function, because f equal to the norm 1 of f minus g equal to norm 1 of f plus minus f minus g1 minus g2, and this is equal to f plus minus g1 plus g2 minus f minus. Okay, so we can use triangle inequality so that this is less than norm 1 of this plus norm 1 of this one. Okay, and all of this is less than epsilon divided by 2, so that this summation is less than epsilon. So the base of this proposition, this proposition that we can prove robust. And we have this definition. Definition of L1R. The notation L1R denotes L1 of lambda, where lambda is Lebesgue measure on either Borel subset or Lebesgue measurable subset. You know that we have two sigma algebra on subsets of R, Borel and Lebesgue. Okay, and Borel set is a subset of Lebesgue set. All of these are subsets of R. Okay, these and these are sigma algebra, and lambda on both of these is a measure, okay, so that R with beta and lambda is a measure space, and R with L and lambda is a measure space too. Both of these are sigma algebra, and lambda on both of these is measure. So that L1 of lambda is the space of integrable function with sigma algebra of Borel set or Lebesgue measurable subset. When working with L1 of R, the notation Nor1 of f denotes the integral of the absolute value of f with respect to Lebesgue measure with respect to lambda. Okay. And the definition of step functions: a step function is a function g from R to R of this form. A step function where I1, I2 and In are intervals, not elements in S, okay, intervals of R, and these constants are non-zero real numbers. Non-zero real numbers. So that a step function is in particular case of simple function, okay? A step function, in a step function, these sets must be intervals. Must be intervals of R. Suppose G is a step function of the form above, and the intervals I1, I2, In are disjoint. Then the norm of G, Nor1 of G equal to this, and we see this for arbitrary simple functions, okay? Arbitrary simple functions. The integral of this f the Lebesgue integral of this simple function equal to this in general, okay? And this is a particular case of that. Even though the coefficients a1, an is in the definition of a step function are required to be non-zero, the zero functions that is identically zero on R is a step function. For C, this take n equal to 1, A1 equal to 1 and I1 equal to empty set. Briefly, we can say that this step function equal to 0 because this is equal to 0. C of empty set equal to, if x belong to, for each x, okay, if x belong to empty set equal to 1, otherwise equal to 0, and we don't have any element in empty set, so that this is equal to 0 for each x. Okay, so that this is equal to 0. Okay, we have approximating by step functions. Suppose f belong to L1 of R, then for every epsilon there exists a step function g by this property. There exists a step function. We see in general case there exists a simple function, okay? For any f in L1 of mu and any epsilon, there exists a simple function g by this property. In the case of x equal to r, we see that for every f in L1 of R and every epsilon, there exists a step function. For the proof, suppose epsilon is greater than 0 by this proposition that we see at the moment, there exists a step function such as this, such that this integral is less than epsilon divided by 2, so that there exists Borel or Lebesgue measurable subsets A1, A2 up to the an of R and non-zero number constants A1, An such that the Lebesgue measure of a car for each k is finite and this integral is less than epsilon divided by 2. Now for each k in this set, for each index k from 1 to n, there is an open subset gk of R that contains a k and whose Lebesgue measure is as close as we want to a k. This by part E of 2.71, okay? Do you want to see this? Let A is a subset of R. All of these are equivalent. A is Lebesgue measurable. For each epsilon, there exists a closed set F as a subset of A with this property. And E, for each epsilon, there exists an open set that contain A with this property. The Lebesgue measure of G minus A is less than epsilon, okay? We use this so that okay. For each k, there exists an open subset gk that contains a k and whose Lebesgue measure is as close as we want to a car, because for each k in this finite set there exists G car as an open subset of R such that contain a car, okay, and the measure of G car minus A car is less than epsilon, and this is Lebesgue measure on R, okay. So that lambda of gk when higher lambda of ak is less than epsilon, so that we can choose gk such that this is less than epsilon for arbitrary epsilon, so that this can be near arbitrary to this, okay. These two real numbers can be arbitrarily near to each other. Now each open subset of R, including each G car, is a countable union of disjoint open intervals. Thus, for each car there is a set E car that is a finite union of bounded open intervals containing G car, whose Lebesgue measure is as close as we want to G car. Please note that since G car as a subset of R is open, we have G car can be written as a union of bounded open intervals, okay, by the definition of open subset of R, okay. Now if we consider these sets, for example, Tm equal to this union, okay, k from 1 to n, then this union equal to this union, k from 1 up to the infinity, and it is equal to G car, okay, for each m in n. And these sets are increasing and converge to G car by this equality. This means that for each m, Tm is a subset of Tm plus 1, and the union of Tm equal to Gk, okay? So that if we consider M arbitrary large, the difference between these two sets is arbitrary small, because for this we see that the limit of this equal to 0, so that for each m, for each epsilon, there exists an m set such that this for each m greater or equal 0, this less than epsilon, and this is equal to this, okay, minus lambda of Tm. So that at first we can approximate this Gk by n Ak, so that this Ak by n open set Gk, that this Gk is open, so that Gk equal to the countable union of bounded open intervals. And in the second part, this Gk can be approximated by Tm, and we know that Tm is a finite union of open bounded intervals, bounded open intervals, so that in the second part we see that each open subset of R, including each Gk, is a countable union of disjoint open intervals. Thus, for each k, there is a set Ek that is a finite union. I write this Ek by Tk, okay? This Tk is Ek of book, and we can this T by replaced by E, okay? I write this Tk, okay? As for each k, there is a set Ek that is finite union of bounded intervals, such that we have this. The Lebesgue measure of Ek minus Ak plus the Lebesgue measure of Ak minus Ek is less than these two, because both of Ek and Ak are subset of Gk, so that this is less than Gk minus Ak, and this is less than Gk minus Ek. And all of this can be considered arbitrary small, so that this is less than this, for example. In other words, the normal one of these two is less than this, because if we consider the normal one of the normal one of EK minus AK equal to the norm 1 of EK minus AK union by EK intersect by intersection of EK by AK minus this AK minus EK union by a intersection of EK and EK. Okay, because EK equal to this and AK equal to this, and these sets are these joints. Okay, these sets and these sets, so that this is equal to norm 1 of EK minus AK plus this intersection minus 3 of AK minus EK plus AK intersect by EK, and these two omitted with others, so that okay, then omitted this by this, so that is equal to these two norms. Okay, so that this norm 1 equal to this summation, and this is less than this positive real number. Now we can see that the norm 1 of f minus this simple function is less than or equal the norm 1 of this minus this by triangle inequality, because it's trivial that norm 1 of this AK EK equal to f minus AK AK minus and plus. We added and omitted this. Okay, so that this is equal to 0, and we write this itself. Okay. Now use triangle inequality. This is less than the norm 1 of this plus the norm 1 of this function. Okay. And this is less than epsilon divided by 2, and this is less than this, and this, all of these less than these positive numbers, so that all of this less than epsilon divided by 2. Okay, if we write this less than AK multiplied by epsilon divided by this, and this summation is less than epsilon divided by 2, whole of this less than epsilon. Okay, and finally we have this approximation by continuous functions. Suppose f belongs to L1, then for every epsilon there exists a continuous function. This is very important. Continuous function g from R to R such that this norm is less than epsilon, and g is almost everywhere bounded. The set of all x that so that the set of all x such that g of x is non-zero is bounded set. This set is n bounded set. Okay. For this, you can see for every constant such as this and any function in L1, we have this by triangle inequality. Okay, you can add this and omit again, add this and omit again, and use triangle inequality. Okay, and this is less than this, it is equal this by triangle inequality 2, triangle inequality 2, where the inequalities above follows from this and this. We can choose these constants to make this norm as small as we wish, because by previous proposition we can use this step function. Okay, this is a step function because these are intervals. Okay, the figure here, this figure shows that there exist continuous functions g1, g2, gn in L1 such that this summation is as small as we wish. Because if we consider this as gk, okay, this or continuous, this is a continuous function. Okay, if we consider these continuous functions, then in each interval we see that the difference of this function and this function only happen in this. Okay, phi of bk and ck equal to 0 on this interval, but gk is non-zero in this interval and also this interval. Okay, in other intervals such as this, gk equal to 1 and this function equal to 1 2. In these intervals, gk equal to 0, the red line. Okay, and also this function equal to 0 on these intervals, so that only difference of these two functions happen in this interval and this interval. Okay, and if we tend this point to bk and this point to ck, we can consider this distance smaller and smaller. It is very trivial. Okay, now if we consider these functions a ka, g ka, we see that we have this property that this can be considered arbitrary small, because it is not that this summation a ka, b ka, c ka, a ka phi of b ka, c ka, ka 1 up to the end, minus this function. This is our function g. Okay, equal to this or a ka, g ka. This is our function g. Okay, a ka phi of b ka and c ka minus c ka. And this is less than or equal this summation. Known one. No, this known one can be considered smaller and smaller. Okay, by this known can be considered arbitrary small, so that whole of this can be considered arbitrary small. Sorry, we can consider this smaller than this. Please note that in this figure that the integral of this function, because this difference equal to 0 on this and this, so that this function is only this plus this on these intervals, and the integral of this function and this function can be considered arbitrarily small, and we see that this summation can be considered arbitrarily small. Okay, please read this proof exactly, and if you have any question, please inform me. Thank you very much, and thank you for your attention. We continue in the next session. Do you have any questions, dear students? Do you have any questions? Do you have any questions? Do you have any questions? Thank you very much. Thank you and goodbye for now. Goodbye.